Okay, so the next thing we are going to have to do is we're going to pick our W and our T functions so that we can actually do the integrals that are required by the C and K and Q and G, right? And what these look like is basically guided by our discretization. So here's our computational domain, and our discretization consists of elements, and the edges of the elements are nodes. So for example, this might be node I, and let's draw some other nodes here. Let's say like this, and maybe one more here and here. So this is node I, this is node K, and this is node J. And we're going to deal with triangular elements. So this will be element E, right? And of course these go out. And our total computational domain sort of looks like this. So this is a computational domain that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. So n is equal to 10 nodes. And this is going to actually be the number of unknown temperatures, right? So our T vector is the temperature at every one of these nodes, T1, which is a function of theta, T2, which is a function of theta, down to T sub n, which is a function of theta. Right, so this is defining the dimension of our system of equations. And these nodes are connected to form elements. And this one has, I guess, if I look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 elements. So n sub E equals 11 elements. So if I'm doing an area integration, which all of these things required an area integration, well, except for this, these three things required an area integration, I'm going to do these area integrations element by element, if that makes sense. So T, we know what T is then. T is the vector that contains all of our unknown nodal temperatures. The function is W, so W, X, Y. These are interpolating functions. Interpolating functions. Okay, we have one of these for every node, and basically they tell you what is the influence of the temperature at that node on the temperature over the entire computational domain. Right. So W transpose looks like this. It's W1, which is a function of x and y, W2, which is a function of x and y, all the way to W sub n, which is a function of x and y. Right. So our approximate solution then, T, which is a function of x, y, and theta, we can write as W transpose times T, and it's just this multiplied by this, so W1 times T1 plus W2 times T2 plus Wn times T sub n. Right? So if I look at what this is saying, you know, here's the temperature at node 1, wherever node 1 is, maybe node 1 sits right here. This is giving me how that temperature influences the temperature everywhere else. Right? So I would expect far from node 1, W1 would be 0, but in the elements near node 1, W1 would not be 0. Right? The same thing for node I. So let's look at, for example, element E. Right? Element E is formed by nodes I, J, and K. Within element E, I would expect Wi, Wj, and Wk to all not be 0, because these are the three nodes that together would tell me what the temperature is anywhere inside of this, especially for the linear elements that we're going to use. These are the only three nodes that we need. You know, if I'm thinking what is W1, inside of element E, it's going to be 0 because node 1, its temperature has no impact on the temperature inside of this particular element. So these are interpolating functions, these guys right here, and they basically tell us how to interpolate values at discrete points and nodes in order to get a continuous solution. We want to think about what the temperature inside of node E actually looks like. We can sort of sketch. So here's T, and this is Y, and this is X. So down here somewhere I have element E, and it's formed by nodes I, J, and K, right? So this is at XI and YI. This is at XK and YK. This is at XJ and YJ. And if I go up, then there's a nodal temperature at node I. So maybe that's all the way up here. This is T sub I. There's a nodal temperature at node K. So this is T sub K. And there's a nodal temperature at node J. So this is T sub J. And the temperature inside of this element is just going to be a linear combination of these nodal temperatures. So for the linear elements we're going to use, you can think of like a plane of glass that the plane is defined by these 3 points, right? The plane is defined by 3 points. This plane is defined by these 3 points, right? So the temperature inside of element E is this plane right here. Right? In fact, this is how we're going to assemble all of our matrices is one element at a time. So the superscript E means the temperature inside of element E. So the temperature inside of element E, well, if I look inside of element E, there's only 3 interpolating functions that won't be 0, right? If I have an element way out here somewhere, right, if this is node M, let's say, node M has some temperature, T sub M, but the impact of this temperature on the temperature inside of here is 0. So the only 3 non-zero interpolating functions are W sub I, W sub K, and W sub J. Okay, so inside element E, I can write T sub E is just equal to Wi times Ti plus Wj times Tj plus Wk times Tk. So all other W's are 0. Right? Remembering that these are the 3 nodes get together to find the elements, and so these are the only 3 non-zero weighting functions inside of that particular element. Okay, so T sub E is equal to be a whole bunch of zeros until I get to Wi, and then a whole bunch of zeros until I get to Wj, and then a whole bunch of zeros until I get to Wk. And I'm going to multiply that by my temperature, T1, T2, T sub n. And so this is equal to this. And the point is that this is a lot simpler than having to deal with all of these, right? So if I just knew the functional form of these interpolating functions now, I could actually do an area integral over this element. And actually then if I want to do an area integral over the entire computational domain, it's just summing up the contributions from every single element. So what does Wi and Wj and Wk look like inside of this element? So let's think about this for a second. If I go back, and this is Y and this is X, and I have I, and then K, and then J. So here's my element, and I could draw any of the weighting functions. Let's do w sub I. So inside of the element, if I'm at node I should be getting T sub I, right? That is the temperature at node I. So that's going to work if at this particular location, at this XY location, Wi is equal to 1, and Wj and Wk are both equal to 0, right? And then as I move from, let's say, xi, so this is xi, yi. If I move from there down to this node, so xj, yj, well, what should happen to wi? Well, wi here is 1, right? The temperature is entirely governed by T sub I. But if I move down this way, here I would expect wi to be 0 and wj to be 1, right? And if I move this way, here I would expect wi to be 0 and wk to be 1. So you can imagine this thing. I guess I should have drawn this a little bit differently, but this is kind of a plane of glass where I start here at 0 and 0, and then I slope up to 1 in this direction, right? So wi varies linearly from 0 to 1 as I move from the other two nodes up to node I. I could do the same thing for wk and wj, right? So let's do just one more. Let's do here's x and y, and this is wk, for example. So here I have I, j, and k. So what is wk going to look like inside of element E? I know that if I'm at node k, it should be 1. Right, so this should be 1. And then if I'm at node I, it's going to be 0. And if I'm at node j, it's going to be 0. So it's going to be this pane of glass that sits here like that. Right? And if I want to think about what does wi or wk look like over the entire computational domain, well, I mean, if I have, let's say, this is node I, and then it is surrounded by a bunch of other nodes, so I don't know what these are, but something like this, however many elements I have. Right, and we can go on and on and on out like this. But what does wi look like? Well, in this element here, I know that wi starts at 1, and it goes to 0 at these two nodes. Right? In this element here, starts at 1, and it goes to 0 here, and then here. So you can imagine this multifaceted pyramid that is centered on node I, where it goes to 1, and then in the adjacent elements it goes linearly down to 0. And then if I go outside of these elements that neighbor node I, wi is 0 everywhere else. Right, so wi you can think of as this pyramid that is centered on node I and extends one level of elements outwards. Okay, so remember that our system of equations looks like this. So c dt d theta, well, this was an n by n matrix, an n by 1 vector, plus k times t, again n by n matrix, n by 1 vector, equals q plus g. And at least this, and this are all related to area integrals. So these are related to area integrals over the entire computational domain. And so we have, whatever this computational domain is, we have a bunch of elements now that we use to define it. And the point is that we're going to do these area integrals one element at a time. So we're going to do it element by element. And these integrals then are related to area integrals of either w sub I, or dw sub I dx, or dw sub I dy. And at this point we know at least what these interpolating functions look like, and also we know exactly which ones are going to be active or on or non-zero inside of each of these elements. Right? So we're constructing C. We'll construct C and K and G element by element. So in this way we're really going to be having to figure out rules for C for any one element, K for any one element, and G for any one element. And then what we're going to do is we're just going to sum these up to get our total or our global capacitance matrix. We'll sum these up to get our global conduction matrix and so forth. And this is exactly what we did for finite differences. The difference is that in finite differences, this was pretty easy because we were just basically filling in row by row by row of C and K and G as we did these different matrices, right? Because a row in C would correspond to a particular node in our solution, right? This is going to be a little different here because a row in C actually does not correspond to a given element; it corresponds to a given node, right? So if this is node I, a row in C corresponds to a particular row in C corresponds to node I, but that actually corresponds to a whole bunch of different elements that surround I. So we'll be doing this, but we'll be adding always to this global capacitance matrix, and we can't forget that. So what we'll do next time is we'll talk about how we do these area integrals element by element. Right? So we have an area integral over the entire computational domain of whatever it is. Right? Depends on which one of these we're constructing. So this is area integral over entire domain. And this is going to be equal to the sum from E equals 1 to the number of elements of the area integral done element-wise. Right, so this is the area integral over some area of an element, and take the same quantity but just evaluated inside of that element. Right. So, and the point is that this is easier to do for a couple reasons. Again, we know that only 3 of our W's are non-zero inside of the element, and then we'll also know exactly what they look like inside of that element. So this is the sum of area integral for each element.